now.
Actually,
Yeah.
sorry, I did notice that Kristen is here.
Okay.
Kristen, are you able to hear me all right?
Yep,
Okay, perfect. Sorry, I didn't see you come into the Zoom room. I had it on gallery mode.
no worries.
This
But
is-
yeah, I'm here. If we want to present, we can totally present now.
Okay,
That's
well, in that case,
great.
Nicholas, does that solve the problem?
Yeah, that will solve the problem. Yes, thank you very much.
No
So,
worries.
Madison, you're on, and Kristen, and you will be talking about 3D printing, obviously. Extrusion on the moon, validation of regolith-based fused deposition modeling in low gravity environment. Madison, the floor is yours.
Thank you very much. And good morning from Canada, everybody. I hope that International Moon Day has been off to a wonderful start for all of you. I'll begin by sharing a presentation in just a moment. But while I do so, I wanted to say thank you. It is our third annual year of presenting for the Lunar Development Conference. And for some of you, I'm very familiar with. I've seen you every single year. And for some of the new faces, welcome. Always happy to see more participation. As we launch into, for us at Space Copy, our third International Moon Day, every time that we have the opportunity to present more about what we're building, the technology becomes greater and more nuanced, as does the pathway towards lunar habitation and everything that encompasses it. So I invite you all today to sit back and listen in to a conversation about 3D printing and additive manufacturing on the lunar surface, more about our state-of-the-art work, more about the long-term vision, and where we plan on encompassing the technology for future growth. So I'll take it away with the talk titled Extrusion on the Moon, Validation of Regolith-Based Fused Deposition Modeling in Low Gravity Environments. And towards probably about the 2/3 mark of my presentation, I will invite Kristen De Loretto to come and give a 5-minute interjection and speak more about her work in ISRU and regolith-derived concretes. But with that, let us get started. So a little bit about me. Of course, for those of you that have listened to me speak for the past few years, this is a rather redundant point. But my name is Madison Feehan, and I'm the CEO and president of Space Copy. Aside from my work in entrepreneurship related to ISRU, I worked for NASA's Planetary Science, Heliophysics, and Astrophysics administrations for 6 years, up until earlier this year. I was a non-civil servant and focused on dual-use technology efforts, a lot of technologies that were in orbit, in cislunar space, as well as technologies that went to the lunar surface. I participated in data analytics as an analyst for the European Space Agency, and I am a member of various different communities, not only the Moon Society, but also GEGSLA, which is the Global Expert Group in Sustainable Lunar Activities, which is a subcommittee advisor to UN COPUOS, or the United Nations Committee on Peaceful Use of Outer Space. So my specialty and background comes from a space policy side, a space business side, and also a science side as well. My education background is in commerce and international business from Harvard, and I'm just wrapping up a degree in Canada, also in business and economics. Lastly, I am the chair of the International Lunar Chamber of Commerce, which is a Toronto-based initiative that focuses on being able to tie in economics with science when it comes to the lunar surface. And I am the region chair of space technology and aviation for the province of Alberta, Canada, which I call home and where I'm calling from here today. So, with that preface, ladies and gentlemen, I want you to kind of think back into your mind. Imagine we're back in 1969, the final lunar frontier, if you will. Apollo 11 astronauts are about to step foot onto the moon surface for the first time in recorded human history. I mean, we had it down to a science for them. We were quite fortunate. We didn't have the amazing technology that we have in present manner. But what would have happened if there was a malfunction and something broke on that lander, and if an electronic control become unresponsive, or some pivotal piece of mission critical equipment that would have put the entire mission in jeopardy? What do you do? Well, for us at Space Copy, and myself as a research scientist, the most logical answer was you manufacture a replacement. which forays us into the art of 3D printing or additive manufacturing. I tend to use those terms interchangeably. There are multiple different types of manufacturing that can be employed on the lunar surface. There are things like casting and subtractive manufacturing methods, but there are also additive methods, and I'll primarily focus my talk on additive, primarily extrusion-based 3D printing. But just to recap it for those who are not as familiar, essentially to create three-dimensional objects, you utilize a digital file or a CAD model that is spliced together to create a render of what you're trying to 3D print. From that, you can use a feedstock or raw material. Generally in the 3D printing industry, you're talking about plastics or metals, but you can expand that theorem to include composites and polymers, things that are carbon-based, things that are ceramic-based, and most importantly to today's conversation, things that are regolith-based, with implementations that are very strong in the medical, automotive, aerospace, defense, and fashion industries already. 3D printing has been around for 4 decades. And ironically, 3D printing of regolith glass has been around for 33 years. So when we talk about 3D printing and additive manufacturing for space, as novel as the technology sounds because nobody's actually done it for a surface operation, this is a technology that has been lab validated for over 3 decades. Speaking now in terms of translating additive manufacturing to space, ISM or in-space manufacturing describes this practice, creating mission-critical supplies, infrastructure, medicine, robotic components, and so many more to support both manned and unmanned missions on orbit and on planetary surfaces outside of Earth. This encompasses LEO, cislunar space, the lunar surface, even some components of GEO as well. The most sustainable and scientifically compelling form of in-space manufacturing, or ISM, uses a process called ISRU, which we've been talking about in great length today, extracting valuable commodities from space to use as raw manufacturing feedstock. I think that a lot of people connotate ISRU as strictly liberating certain minerals and certain properties from lunar regolith, but it can also extend itself to, for example, utilizing space debris as a form of feedstock for additive manufacturing. So it's important to keep in mind that there are diverse applications. We must not limit ourselves. Now, specifically for lunar construction applications and even extending itself towards Martian construction, regolith is able to be easily, in some senses of the word, extracted, processed, and melted and fused together through 3D printing and additive manufacturing technology. Now, why this is important, not just because of the science aspect, but also from the economic aspect. So if you allow me to put my business cap on for a moment, the space economy has a valuation right now, as of 2024 anyways, of 464 billion US dollars. This is slated to increase to over 730 billion by 2031, and I would like to revise the figure in my presentation, 1.4 trillion US dollars by 2040. Now, the lunar manufacturing market comprises a small but dedicated piece to this marketplace, valued at 1.5 billion as of 2023 and slated to increase to 7.5 billion by 2030, and then increasing from that point forward by around 1.5 to 1.8 per annum over the next decade. The lunar economy is recognized right now globally as one of the most fast-paced growth-induced economic markets since the dot-com bubble. So we have an opportunity to set the precedent of what the future looks like in space by building technologies and by having conversations like this to spark innovation and to make action happen. And the next generation of spaceflight can only be safely conducted if in-space manufacturing is widely developed and utilized. Now, this notion is not just recognized by me, it is recognized by global industry leaders in aerospace in the form of government, academia, and industry. I find it quite quaint to note how government, industry, and academia does tend to work together, and I think that we've reached a turning point or an inflection wherein it has become necessary for these entities to look for pathways towards collaboration because the mission itself has become too large to do independently. One of the big reasons that I found when working as a non-civil servant for NASA was that the reason that we had small businesses in space technology in the first place was because of the fact that the market had become so large and the government annual budgets had become so small that we were not able to properly compensate for what we needed to do to get the job done. And that has introduced an entirely different ecosystem and given opportunities to people to participate in space in places where they might not have in the first place. And that is people that come from a technical background and a non-technical background. I always say there's a place for space for anybody that is interested and passionate in the subject matter. Now, speaking of subject matter, you might be wondering who Space Copy is. If you haven't heard one of our talks before, we describe ourselves as an in-situ logistics and additive manufacturing company based in the United States and Canada. When I say United States, I mean California. When I say Canada, I mean Alberta. Alberta is one of those places in the middle of nowhere that is rather cold most times of the year, so I don't expect most people to know where I'm talking about. But we also have expanded in our past year. We've expanded and created 2 joint venture projects in Europe, one out of Paris and one out of Warsaw. Either of those projects I will speak to briefly today. But I will say that one has to do with drones manufacturing for aviation, and the second has to do with liberation of oxides from regolith during the melt phase to support astronaut life support systems. Speaking in term, we are not just a space company. We are a company that services manufacturing for defense, aviation, mining, energy, oil and gas, and primarily we want to focus on clean and renewable energy resources, but we're able to provide manufacturing infrastructure to austere climates, both on Earth and in space. So natural disaster areas, construction sites, areas affected by war and combat, for example, as well as places like the Arctic, desert, and ocean floor. And it gives us an opportunity to work in these extreme terrestrial environments as an analog precursor to what we expect to find in space. And in doing so, we're able to give back to many underprivileged, remote, or austere communities and give them back the infrastructure that they need in order to build out their economies locally. So I do tend to kind of offer this as an interactive question to audiences, but does anybody know here what the current launch cost is to send 1 kilogram of supplies from Earth to the moon? If you'd like to raise your hand and try and answer this question, go for it. If you'd like to put it in the chat, go for it. If you would not like to do any of the above, I will tell you, but I will give it a quick 10-second pause to see if anybody wants to participate. Right. Matt, I appreciate your enthusiasm. I wish it was that cheap. Any other takers before we move forward? I'm going to use NASA launch costs, by the way, not the astrobotic ones, but I will talk about both. All right, going once, going twice. All right. Now, we do hope to get to Matt's estimate of $6,000 per kilogram, and I do think that in some degrees, depending on your position on SpaceX, we will get to that point. But right now, NASA estimates this at $1.2 million for every kilogram of supplies sent from Earth to the moon. In doing so, I mean, there's astrobotic estimates that characterize this as $400,000. There's NASA that characterizes this as 1.2 million. There's Elon that characterizes this as $10,000. Depending on your context and what you expect to find, I mean, this launch cost is going to vary if you're talking to industry versus academia versus government. But right now, I will err on the side of caution for what it's cost in the last 5 to 10 years, which is 1.2 per kilo. Now, taking all of this into mind, this necessitates a lot of the use case for doing additive manufacturing on the lunar surface. Right now, we're planning the Artemis missions, for which I'm very proud that who's considered to be a local astronaut, a fellow Canadian, is part of. In that sense, 4 astronauts planned for Artemis would require just under 22,000 kilograms of supplies needed to sustain themselves as a crew for 1 year on the surface. And at $1.2 million per kilo times, say, 21,700 is around $6 billion just in critical infrastructure costs. Now, taking this into play, it's not as if lunar economies or even the American economy in itself cannot sustain that kind of cost metric. It is still within the wheelhouse, but it is unsustainable, and there carries not just the risk and cost, but the risk in transportation, in weight, and the overall merit of justifying this to a fiscal budget. Therefore, additive manufacturing has presented itself as a viable solution. And when I say solution, I like to characterize this as 70% of the solution. 3D printing represents a cost savings of 70% of that launch cost, 70% of that $6 billion at 20% faster speeds than you would have had deploying commercial technology regularly from Earth to the surface. Essentially, when you do your first landing, when you have your first manufacturing system or fleet of manufacturing systems, if you're trying to build an empire, you have the capability of being able to work with the resources that are on site. And that gives you a foray into being able to build much faster, much smarter, and much cheaper. And then again, I will just take 1 second to denote that the remote locations on Earth, primarily again, desert, Arctic, ocean floor, they have limited infrastructure. They face challenges similar to space. They also face challenges in the form of legacy equipment, so pieces of critical infrastructure that are no longer manufactured by their OEMs. This costs innumerable amounts of money, but in some cases it also costs lives. Harsh weather drives the costs up for living, and nobody knows that better than a bunch of Canadians that are trying to put 3D printers on the moon that live in one of the colder places of the country. I'll denote a little bit later how we are going to be launching our first systems into an analog astronaut test site, but for now, let me carry forward and talk more about the use cases of extrusion-based manufacturing in lunar and relatively low-gravity environments. So a lot of us know it already, 16G on the lunar surface, abundant in its mineralogy for regolith. You have your highlands, you have your mare. Primarily, highlands boasts itself as the more natural feedstock, in my opinion. It bears a constituency of around 48% silicon dioxide, which gives us pause and gives us something to base ourselves on, so that we can manufacture in similar context to ceramics. If I were to explore this slide a little bit deeper, I'm going to talk about regolith simulant, but to characterize this even further, regolith itself, simulant or not, does tend to bear recognizant properties of working with ceramics. There is around a 10 to 12% give or take when it comes to metal composition, maybe around 1 or 2% quartz for South Pole Highland simulants. And what we did at Space Copy is we took Raman data from the Changi 5 mission and we converted that into as much data as we possibly could. And we compared that between two particular simulants. We compared it to Marshall Space Flight Centers or Washington Mills, LUT, I want to say LUT, H&W, but I think I'm mixing up the acronyms. The Washington Mills simulant 5M, as a lot of people refer to it as, and the off-planet research OPR H2N simulants, both of which are highlands and are recognizant to Apollo 16, which is the closest that we've been able to estimate to the lunar surface, particularly the South Pole. And from the slide or the picture that you're seeing on the right-hand side of this slide, you can see some of the mechanical properties. Now, we're still working on geotechnics. I do believe that that can always be improved, not just in particle morphology, but also in mineralogy. But from a mechanical point of view, we do estimate that we've achieved around a 97 to 99% accuracy in its bulk density. Aside from this, though, we are not working with standard simulants at Space Copy. We are actually reverse engineering some of those mineralogies with the folks at Off Planet Research to create something that's customized. And this is where I come back to us having used the data that came from Changi 5. We tried to create as best of an estimation as possible so that as we're doing our extrusion and melting, because we do both, 3D printing testing in our R&D labs, both in Canada and the United States, we were aiming to ensure that we had the highest degree of accuracy before we move into an analog site. Now, key projects for lunar infrastructure development. If it's not already obvious, we have to phase this into multiple different iterations. This is not going to be a one-stop mission to the surface, but starting with critical pieces of infrastructure, launch pads, roadways, blast shields, pipes, repair parts, simple tools, and interlocking bricks that can be used for habitation are going to be the primary efforts of any company that does in-space manufacturing, particularly on the surface, and it is going to be our primary objectives. We're going to be talking a little bit later today about regolith-based concretes, and that ties in very closely to extrusion technology. I had the privilege of working with a university in New York to create geopolymer concrete materials from regolith. And this is not a photo of it. This is a much more nuanced and much more carefully derived type of regolith concrete that you're seeing on the screen that comes directly from Marshall Space Flight Center's MMPACT lab. Led by Jennifer Edmondson and Corky Clinton. What you're seeing here in this picture is a depiction of a solid printed cylinder from an extrusion-based technology. You wouldn't know that because it looks absolutely perfect. You can't even see the lines of that extrusion. I do believe that there was some post-processing and finishing done on this part, but if anything, I want this visual to characterize for all of you that it is indeed possible to do extrusion and any type of additive manufacturing on the surface. Now, speaking in terms of a space copy, we have employed a 4-stage additive manufacturing technology that is interchangeable between both extrusion and laser powder bed fusion. The matrix does not change, but the process does. The 4 stages in which we've encompassed our strategy towards 3D printing on the surface first starts with particle beneficiation or benefaction. A less technical term of this would be just mixing, wherein we are crushing, mixing, and sieving the raw regolith particles into a semi-homogeneous feedstock that is more rounded in particle shape and size to reduce abrasion. Whilst doing so, we conduct processes like annealing, and we use laser sources to try and treat the regolith in an effort to reduce electrostatic charge. We aim to operate both during lunar day and lunar night, but I will be speaking mostly in context of lunar day. For stage 2, we move into feedstock sampling, wherein we are utilizing spectroscopic diagnostic tools to assess from a non-destructive perspective the mineralogy of the regolith. So if there is anything that is different in characterization than what we predict. Once we're able to obtain this mineralogy data, we plug it through AI agents built into the software of our 3D printers, and that allows us to have smart, optimized process parameters. Which carries us into stage 3, which is the 3D printing itself. So I talked about laser powder bed fusion and extrusion-based technologies as viable and as within our pipeline. For now, what we predict to be the first surface technology that we deploy would be the extrusion technology for fused deposition modeling or just FDM printing. Very good at creating rapid supply infrastructure. There was a 4th item on that matrix, but it's better described when you're looking at a schematic diagram of the printer system. So this is a large one. We're also developing out something that's CubeSat size that we can use for early stage testing. We have a cislunar flight test mapped out for the end of 2026, and we're still doing some technical risk mitigation in our early prototypes. But this schematic design showcases something that is highly unique, and that's automation. Assuming that you don't have astronauts on the surface, it is important to take into account how much maintenance, how much operation, and how much downtime that you have in a technology like this. And I'm proud to say that our team has been working on building out software that is capable of managing the system fully autonomously, from material processing to 3D printing to post-processing. And when I say post-processing, I would like to introduce one other core piece of technology, and that's automated robotics. We have a robotic arm located in the center of the 3D print chamber that is responsible for carrying out post-processing and quality assurance efforts. And I will wrap this kind of matrix-like discussion on how the technology works by saying that this is fully patented, fully trademarked, and already in development and preparing for operation within the next 8 to 12 months in the Canadian Arctic. So for a few of you that are not as nuanced in additive manufacturing technology, if you're questioning what I mean by laser powder bed fusion or selective laser melting, also known as SLM, versus extrusion-based technology, or FDM, I would suffice it to say that extrusion-based technology is more along the lines of creating a slurry, and building out infrastructure, kind of like building out concrete. A more simpler term of this would be to take a nozzle head, so the extruder of the FDM printer, and make a slurry that you can build up from, almost like icing a cake. Laser powder bed fusion in juxtaposition is highly different and focuses primarily on building things downwards. So having a powder bed, running a laser over that powder bed from the shape of your CAD model, and then running a recoater blade over that initially sintered or melted line, and then building downwards from that point. So the powder bed would become significantly lower over time, and the laser would essentially just have to keep melting in place while the recoater blade continues to allow you to build from that structure. I noticed that we have a hand raised from Frank. Frank, did you want to ask your question before I carry on with my presentation?
Actually, I was going to ask when you were going to be finished. I wouldn't want to push people over. I got like 4, 5, 6 questions. One thing that I really wanted to touch on, given that you're here and that you seem to be pretty knowledgeable about 3D printing, is that there's been a development recently in FDM that has been really catching my attention. It's the ability to print objects that are longer than the print bed. I had the CR30 at home, and I made this thing. It's like really big, and I think it shows a lot of potential for Lunar applications, but we'll be able to touch this. I mean, we can discuss this further some other time. I wouldn't want to step on anybody's toes.
Happy to. And ironically, your question couldn't come at a better time because my next slide talks about what we can 3D print with the FDM systems. So I will answer that. And then if by some chance we don't get a chance to really tackle all the questions, I'll drop my email in the chat. From that, our current FDM system that we're building up in Canada has a 1 cubic meter print capacity, so you can print anything up to a meter in size. From that, we have about 250 items that we can 3D print, including items from this list. So again, I talked about kind of the simple structures like precision tools and launchpad tiles, blast shields, and interlocking bricks for habitats. But we can also look at things like pipes, turbine blades, O-rings. We're even exploring, this is more on the melting technology side as opposed to extrusion, but we're even exploring building out textiles from interwoven regolith fibers when combined with a more common fabric substrate that we have validated so far to be radiation resistant and moisture wicking, so that can be used as an insulation material to astronaut suits. So in answer to your question, it's a very, very diverse portfolio. I'll kind of run through some of these slides quickly because I feel that some of them are talking about the same subject matter over again, and I don't want to waste precious time talking about the same thing twice. I will say that if I were to take 4 particular lifecycle management features and benefits to using extrusion technology on the surface, I would like to denote them as speed, ease of use, flexibility, and cost savings. I already talked about the economics of this and where the space economy is building itself towards, so I will not touch on that subject too much further. I will, however, touch in depth on the subject of limitations and tolerances for extrusion-based technology, because as fantastic as it is to have this kind of tech in front of us, it's not easy. Now, low gravity and vacuum effects, everything. It is absolutely a negative denotation. Being able to prevent nozzle clogging because of the altered material flow in 1/6G, or even worse, complete microgravity if you're doing this in LEO. It puts a lot of pressure dynamics onto an extrusion-based manufacturing system. We solved this by having a vacuum integrated into the chamber so that you're creating your own kind of internal environment in the build chamber. But even then, it's not a perfect process, and we have to be recognizant of that fact. Extreme thermal cycling, so thermal gradients being anywhere from, positive or negative 120 degrees, maybe even a little bit wider than that. You could even say positive 120 to negative 150. Induces a lot of die stress, tool fatigue, and product warping. Delamination is common even in ambient conditions, and if you can imagine doing so in a space-based environment, having active thermal management becomes absolutely essential to maintaining those dimensional tolerances. Now, regolith dust, I do tend to say that it is more chaotic in a laser powder bed fusion setup as opposed to extrusion, but we still have to be, again, we're cognizant. Abrasive particulate accelerates dye wear and clogs nozzles. It affects optics if you have cameras and thermal systems integrated into the build chamber to assess what's happening in lifetime. And it demands highly sealed systems, hardened tooling surfaces, and a lot of passive dust mitigation coatings like NASA Goddard's Lotus leaves. There is a lot of autonomous monitoring and energy constraints that are also taken into effect that has to consume itself with power availability. If we're looking at basically the two options that we have in front of us, nuclear or solar, it is more readily feasible to assume that solar is going to be the technology that we use for power supply over the next 5 to 10 years before we are able to take things like the thorium Belkovich crater on the dark side and convert that into, say, sustainable nuclear energy. And in doing so, you need to have as much autonomy and as much independence on a system like this to be able to sustain itself. And we do so in carefully practiced methods so that we're only using 1 to 2 kilowatts per energy each hour, but even then, it's quite a lot of energy. TRL scale on the technology that we're building for extrusion as somewhere between a TRL 4 and a TRL 5, but I'll keep it to 4 for today. And what you're seeing here on the screen are examples of things that we have 3D printed with different regolith simulants. We've worked with Mare, we've worked with Highlands. Most of what you see here is the custom regolith simulants that we developed alongside off-planet research. And the little images that you see with red laser beams, those are on the laser powder bed fusion side, and then everything else that you're viewing has been created from extrusion-based technology. We managed to create a kind of tolerancing point internally to maintain a minimum of 74% density in anything that we 3D print. And we are continuously going under mechanical testing to assess the viability of what we're 3D printing. So you can see the layers in this large brick on the right-hand side. So this is directly coming from a rather large piece of extrusion technology. We partner with many different universities and government and private industry leaders to help us carry out this testing. For example, Johns Hopkins Extreme Materials Institute helped us do some micro CT testing and is letting us use their high fire chamber in 2026 to conduct a simulated micrometeorite test to see if these bricks withstand themselves when having particulate shot at them at around 7 kilometers per second in a 2-stage light gas gun.
5 minutes left, Madison, and I think I've given you a bit of bonus now.
Thank you. Sorry. I will wrap up my thought and then I'll turn it over to Kristen to finish. Wrapping up that thought for what we plan to do for future testing, now that we've validated that this technology works, we validated that the beneficiation technology works, as you can see here on the screen, we've reduced particles down to a micron size in as little as 3 minutes. Now that we know that this technology works, we are going to be deploying this prototype to the Canadian Arctic at the FMARS base in Nunavut, which is part of the Arctic Circle. And if I have one photo of it, yes, I do, for the Arctic field test that we plan on doing in 2026 for the summertime, which will be a prerequisite to our Lunar spaceflight mission, and then eventually get something onto the surface, maybe around 2031. So I think I've talked enough. I'm going to actually pause my screen share for just a moment so that I can exit out of full screen mode without you guys seeing all of my tabs, and I will turn it over to Kristen to give a conversation about what she's working on right now. So Kristen, I invite you to introduce yourself briefly to the audience and tell us more about your extrusion technology.
Thank you. Thank you again for this. My name is Kristen DiLoretto, and I'm a recent graduate of McMaster University, achieving a bachelor's in mechanical engineering. And I personally have experience working on satellites, rockets, and now parabolic flight experiments. I have a strong interest in research and development, and as an engineer, I enjoy looking into the design, analysis, and testing of aerospace systems, but I also love manufacturing and assembling them myself as well. I'm actually currently working as a CNC machinist to help improve my machining skills. The image beside my headshot is actually of a module that I manufactured myself for the project I'll be speaking about today. Now, for some quick background, I think we are all well aware at this point that the next next step of space exploration will involve construction of infrastructure to house humans and resources on the moon, with ISRU being strongly recommended for these future space missions. One strategy of using the moon's resources is to create a regolith concrete or composite. Different binders have been explored, but polymer concrete will involve mixing an organic polymer with lunar regolith and is a promising candidate for very early lunar applications. Now, to facilitate the transportation from Earth, the binder content of this mixture should be significantly reduced. We also need reliable ISRU processing techniques to be developed, and further research is required to understand the properties of this regolith-based cement before it can be used. Next slide, please. That would bring us to my project. The McMaster Engineering Reduced Gravity Capstone Experiment is one of 4 groups participating in the 8th flight campaign of the Canadian Reduced Gravity Experiment Design Challenge. This project is in partnership with the Canadian Space Agency, the National Research Council of Canada, CEDS Canada, and is sponsored by companies such as MDA Space. Our research project will fly on board the Falcon 20 aircraft and will experience a series of parabolic maneuvers to both test and validate the apparatus in lunar gravity conditions. Our experiment involves the design of an automated system that will produce concrete samples suited for 3-point bend testing. Samples will have varying amounts of binder content and then will be compared to samples produced on Earth. The results of our experiment should demonstrate to the extent that binder content can be reduced while still making a suitable construction material. Our flight is happening this November, and we've been continuing development of this project for 2 years. If there's any interest in learning more or even supporting our project, feel free to reach out to me on LinkedIn for some more details. Thank you.
Thank you, Kristen. And I will just wrap up that presentation today by talking. I'm going to skip through the technology demonstration because that is a very, very long demonstration. You can see it on our company website. I will bump all the way past and just leave on this slide, which is collaboration opportunities. And I'm going to say this both for early career professionals that might be on this call, but also for more seasoned experts. Additive manufacturing for space is challenging. It is not something that we will achieve overnight. I've personally been researching the field for 8 years now and have operated a business that will be helping to de-risk these challenges for 3 years. We offer internships for early career professionals that want to have hands-on opportunity to work with our additive manufacturing tech, and it is a remote program, so you don't necessarily have to relocate to the cold part of Canada to do so. And then in parallel, we also give research projects and partnership opportunities for those in private industry and academia. So I want to thank the Lunar Development Conference for hosting Space Copy for the 3rd year in a row. We're extremely honored. And if you are fascinated in learning more about this technology, then I highly encourage you to reach to me. I'll post my contact information in the chat, or you can visit spacecopy.com. Thank you, everyone.
Thank you. Thank you, Madison and Kristen. And unfortunately, we do not have time for further questions here, so those have to be in the chat or by exchanging emails, of course.